In this related rates example, we've been given a swimming pool which is shaped like a rectangular-based prism. Its length is 15 meters, its width is 8 meters, and it has a uniform depth of 1.2 meters. It should be noted that most of the questions that you will encounter regarding swimming pools in this section are not rectangular-based prisms and require a little more work than this particular example. But this is an important example that we have to look at and discuss the implications of the final answer. Well, what I've done is started by drawing my rectangular-based prism, or my swimming pool, and then using the green marker, I've tried to show the height of the water increasing with respect to time. So if you can visualize this, you should note that as I fill this pool with water, the volume of water is changing, as well as the height or depth of the water. However, the length and the width remain fixed. The length is fixed at 15 meters, and the width is fixed at 8 meters. That's not true with the height and the volume. They are changing. Well, what rates of change have they given us? They gave us the value 3 meters cubed per minute. Well, that represents dV dt. They ask us to figure out how fast the depth of the water is increasing when the depth is 0.4 meters, and then later when it's 0.7 meters. So in both cases, they're asking us to find dH dt. So that's our unknown. Well, the next thing we need to do is find an equation that relates volume, length, width, and height. Well, we know for a rectangular-based prism that the volume is equal to the length times the width times the height. So I write that equation down. Now, because our length and our width are fixed, and only because they're fixed or constant, can I substitute 15 in for the length and 8 in for the width. So I end up with V is equal to 15 times 8 times h, which then, when expanded, gives me V is equal to 120h. If you take a look at that function, you should ask yourself, what type of function am I dealing with? Hopefully you'd answer that it is a linear function. And we know that rates of change along a linear function are constant. So I don't think you're going to be surprised by our final answer in this case. Well, I'm going to differentiate both sides of the equation with respect to time. That means we have to use implicit differentiation. So the derivative of v with respect to t would be dv dt. So that's what we have on the left-hand side of the equation. On the right-hand side of the equation, we would have 120 dh dt. That's the derivative of 120h when it's taken with respect to t, time. Now, what I'm going to do is substitute in the values that I know. I know that dV dt is equal to 3 meters cubed per minute. So I fill that in. And when I do so, I realize that there's only one unknown, and I can rearrange and solve for dH dt, and I obtain 0.025, and the units of measure in this case would be meters per minute. So this is my rate of change of my height or depth with respect to time. What you'll notice is that expression doesn't have a value of h that I must substitute in such that I can find a particular rate of change for a specific height. My rate of change in this case is constant. So when I'm asked how fast is the depth of the water increasing when the depth is 0.4 meters, my answer is 0.025 meters per minute. When asked how fast is the depth of the water increasing when the depth of the water is 0.7 meters, I'd get the same answer, 0.025 meters per minute. Our rate of change is constant. And that's what one would expect for a swimming pool that is shaped like a rectangular